Now, for the current density, for the free electron case, we have the current density equals minus NeV, where N is our conduction electron density, number of conduction electrons per unit volume, E is the charge, V is the drift velocity. So if we generalize this to Bloch electrons, what would be the velocity of those electrons? It's given by the group velocity, d omega dk, which is 1 over h bar, the derivative of the energy band in which the electron resides with respect to the wave vector k. Therefore, for the total current density, we would have minus E divided by volume, sum over all occupied states with wave vector k, velocity of as a function of k. So this is the generalized version of the current density for Bloch electrons. Now, we realize that the volume of k space per allowed k value, so that is the volume occupied in k space by one quantum state of the electron, is 8 pi cubed divided by the volume V, which is Lx, Ly, Lz. So this is the volume of the direct space lattice. And these k values were found by using periodic boundary conditions 2n pi over L. So therefore, we have one quantum state in each volume 8 pi cube over V in k space. So this is actually the volume occupied by one state. So we can replace the sum by 1 over delta k, sum over k delta k in the limit delta k goes to 0. So this is going to be in the limit delta k goes to 0. This will be basically 1 over delta k is v over 8 pi cube integral dk. So that's how we replace the summation for this limit, and taking into account spin degeneracy, the fact that we have two electrons allowed per quantum state, one spin up and one spin down, the current density will be minus E integral dk over 4 pi cube velocity as a function of the wave vector k. So if a band is completely full, we would have j is equal to minus E integral in the first Brillouin zone dk over 4 pi cube h bar dE dk equaling to 0. Why is that? Because if you look at the E versus k relationship, it is symmetric around k equals to 0. So the area under V of k vanishes, as you can see here. So we find that filled bands do not contribute to the current, only partially filled bands will contribute. Now this brings us to the concept of hole. So the contribution of all the electrons in a given band to the current is minus E integral dk over 4 pi cube V of k, but a filled band gives no current. So we're going to have the integral over the full zone dk over 4 pi cube velocity as a function of k equaling to integral over the occupied states plus the integral over the empty states. So we can see that because the sum is equal to 0, the current density can be written also as instead of minus E integral over occupied states plus E integral over empty states dk over 4 pi cube times the group velocity v. So the electrical current due to the charge carrying electrons occupying a set of levels in a band is can be regarded as being equivalent to the current that would be produced by particles of positive charge occupying the rest of the levels of the band, which are the empty levels of the band. So those positively charged fictitious particles, we call them holes. And there's a good analogy for this. If you consider a bottle full of water, when the bottle is turned upside down, it is equivalent to say water molecules are moving down or air molecules are moving up. So that's the same situation here. Now, we have a remark. It is important to note that if the current carrying particles are regarded as electrons in a band, the unoccupied levels do not contribute to current and vice versa. So you can see that from this equation, we either regard this current as being due to the occupied states or due to the empty states that are occupied by holes. There is one way or the other to look at this. Now, we usually consider the current carriers as holes if the band is almost completely full except a few missing electrons. So when we consider this energy bands, for example, if you have an electron in the conduction band and a hole in the valence band, we have to be careful with this concept of effective mass here. Effective mass, remember, is h bar square divided by the del square k of energy band E of k. Now, for this electron in the upper band, this curvature is positive, so the electron will have a positive effective mass. However, if you had an electron in the lower band at the same location, you would find that the curvature is negative, so the effective mass of the electron would be negative. But on the other hand, if we regard this as an empty state, so that is a positive charge occupying the state, because these energy diagrams are drawn for negative charges, electrons, a negative curvature for an electron in the energy diagram would imply a positive curvature for a hole. So we would see that whenever we look at these energy band diagrams, the way to get this correctly is to consider an electron at the location of interest in the K space, and then take multiply it with -1 in order to get the effective mass of the hole for an empty state at the same location in K space. So electrons on top of the valence band have a negative effective mass. Holes on top of the valence band will have a positive effective mass. Now, holes have positive charge, so when you apply an electric field to the right, we will see that the electrons will be traveling to the left, producing a current to the right. On the other hand, holes will be traveling to the right, creating a hole current to the right. So we have to be careful with the contributions from electrons and holes when calculating the total electrical current. Now, there is a nice picture to look at this. It's called the bonding model. So in the picture of semiconductors bonding model, for example, if we consider silicon makes covalent bonds and it has a diamond lattice, if you will remember. So if we have one of the silicon atoms replaced by a boron, which is from column 3, but silicon is from column 4, boron unfortunately does not provide the necessary electron to one of the silicon atoms nearby, so therefore it creates a hole. So there is a missing electron. So this missing electron basically implies that this hole can, when we apply an electric field, this hole can travel, or this missing bond can accept electrons as they travel in the lattice. So boron acts as an acceptor. On the other hand, if this were arsenic instead of boron, which is from column 5, which provides an extra electron, arsenic is a donor, so it's going to donate electrons to the conduction band. So boron donates holes to the valence band, and arsenic donates electrons to the conduction band. It's acting as a donor. So these impurities will basically determine the type of conduction in this structure. Now, when we break a bond and release an electron to the lattice, The energy that is required to break this bond and bring the electron from the valence band to the conduction band is called the energy band gap. So that's the amount of energy we have to provide to release this electron to the lattice. So all the electronics industry is based upon this flexibility to tune the resistivity of semiconductors by doping with impurities. So this is called doping process. And you can find out more about this in the course Semiconductor Device Physics, Physics 391, 392, or Advanced Physical Electronics courses, Physics 689 and 697.